Let's now move to some techniques for memory allocation, and let's start with contiguous allocation. So we know that the main memory contains the operating system itself and then the processes of the users. So now we are going to try to answer this question: how do we allocate memory efficiently? And we start with contiguous allocation and then also go into segmentation and paging. We will see that there are trade-offs, of course, as always. And actually, what I want you to put attention to is that you will see that the more we get to, let's say, complicated memory management techniques, basically paging and virtual memory in the next lecture, the more we separate logical from physical representations of memory. And this has a lot of benefits. There is less fragmentation, we use memory better, it's easier to protect the processes, and it also results in faster loading and swapping of processes. We will see now these things one at a time. So let's start with contiguous allocation. This is the most basic thing you can do. So you put the operating system at the bottom of your memory, and then one process after each other, giving each process a contiguous set of addresses. Okay, this is just an example with 3 processes and the operating system. Okay, this would be the physical memory. So now each process has its own logical addresses. They start at 0 and they go up to a certain number. Okay, and when we are running, let's say, process A, and A wants to access a certain logical address, which in this case will be an offset, we check whether this is less than the limit for the process. If no, then we can wake up the operating system so that it takes care of this process that is trying to access memory that does not belong to it. If yes, then we sum the relocation register, or the base, basically a register that contains the first address of process A, the first physical address of process A, and then that the CPU can access the memory and read, write in the physical address of the memory because it is safe, it's accessing its own memory. Pretty easy, but of course, as we discussed before, uses stuff as always a cost, and let's see what the limitations are. When we terminate a process or we swap out a process, we leave a hole for that process. You need to keep track of which holes are available at all times. The operating system needs to do that for other processes. And this results in potentially external fragmentation. What does it mean? That it might be that if we look at all the space we have available, so the sum of the sizes of all the holes, we have enough free space to put a process in memory. The problem is that if we look at the individual sizes of the holes, there is no single hole that is big enough to contain the process. Okay, so the major limitation here is that if you want to run a process, but there is no hole that can contain such a process, then basically you are done. It might be that you have a lot of free space, so indeed you could run the process if you just look at how much space it needs, but in practice you cannot. Also, you need to think about how you take decisions when it comes to assigning processes to holes. You can take the first that is available, pretty easy, the first that is big enough, of course. You can try to find the best fit. So basically the smallest hole that is big enough to contain the process. The good thing if you do this is that you this algorithm produces the smallest leftover hole. Okay, but of course you need to search now. So searching for something will take more than just taking the first element. So going back to the pros here, it's basically you don't waste a big hole to put a process that is actually small. If you go to the worst fit, the opposite, then you try to look for the largest hole, and this will produce the largest leftover. Okay. But again, the price you pay here is that you need to search the entire list again. As we will discuss more in the future also for file system, one of the complications here is that you don't really know which strategy is the right one or the best one until you actually start running the system and discover how many processes you want to run and how big they are and how many holes you have. So there are different techniques you can use. The problem is that you don't really know which one is the right one, because to get to know that, you need to first actually run the system. And to run the system, you have to take first a decision about which strategy you are going to use. So you see that there is like a conceptual loop here, loophole, that makes stuff complicated when it comes to taking decisions for the operating system and how it manages memory.